Continuity and the intermediate value theorem. The intermediate value theorem will be referred to as IVT. Please write down this definition of continuity. Y equals f of x is continuous at x equals a if f of a exists. The limit of f of x as x approaches a from the left equals the limit of f of x as x approaches a from the right. And when these left side and right side limits equal each other, then the limit of f of x as x approaches a exists. And the third condition for continuity at x equals a is the f of a which exists and the limit of f of x as x approaches a which exists, those have to equal each other. The f of a and the limit of f of x as x approaches a have to be equal to each other. Make sure you pause the video to get all of this written down. Then you'll need to write all of this. There are types of discontinuity: removable discontinuity and non-removable discontinuity. The discontinuity at x equals some number is called removable if the limit of f of x as x approaches n exists. We remove discontinuity at x equals n by setting f of n equal to the limit of f of x as x approaches n. There are two types of non-removable discontinuities: jump and infinite. When the limit of f of x as x approaches n from the left and the limit of f of x as x approaches n from the right are not equal, we're going to have what's called jump discontinuity at x equals n. And we have infinite discontinuity at x equals n if the limit of f of x as x approaches n from the left is equal to infinity or negative infinity, or if the limit of f of x as x approaches n from the right is equal to infinity or negative infinity. Both of these, jump discontinuity and infinite discontinuity, are both non-removable discontinuities. The infinite discontinuity at x equals n will be when x equals n is a vertical asymptote. Make sure you get all of this written down. Pause the video if necessary. This is an example of a function that has a removable discontinuity. This function, x squared minus 4 divided by x minus 2, is discontinuous or not continuous at x equals 2 because f of 2 does not exist. Replace x with 2 and you'd have division by 0, which is impossible. But this discontinuity is removable by setting f of x equal to 4 when x equals 2. In other words, if the function is rewritten like this, it is a piecewise function. make f of x equal to x squared minus 4 over x minus 2 if x is not 2, and make f of x equal to 4 if x is 2. This new function makes us plot the point when x equals 2, y equals 4. And when I plot that point, we now have a continuous function. This is an example of a function that is discontinuous. At x equals 2. For the same reason, it's because f of 2 does not exist, but it is impossible to remove the discontinuity. It is a non-removable discontinuity. At x equals 2. In the last one, we removed the discontinuity by simply adding on the point 2, 4. That filled in this hole, or the discontinuity. Here, if we fill in this hole, the function is still discontinuous. Or this hole, the function is still discontinuous. If we connect these with a vertical line to make the pieces connected, then it's not a function anymore by the vertical line test. So non-removable discontinuity is when the limit of the function as x approaches 2 from the left is not the same as the limit of the function as x approaches 2 from the right. The limit of this function as x approaches 2 from the left is actually -1. And the limit of the function as x approaches 2 from the right is actually +1, and those are not equal. This function is discontinuous at x equals 2 because f of 2 does not exist. It is also not possible to remove the discontinuity because the limit of this function as x approaches 2 from the left, you can see, is -infinity. And the limit of this function as x approaches 2 from the right, look over here to the right of 2, is way up here, +infinity. The discontinuity is called non-removable. And to be more specific, it's called infinite discontinuity. At x equals 2. To say there's infinite discontinuity at x equals 2 is the same as saying there's a vertical asymptote at x equals 2. So non-removable and infinite. Non-removable, this one, by the way, is called a jump discontinuity. At x equals 2. And this one is a removable discontinuity at x equals 2. Here's an example. Determine the value of k see where the k is, so that this piecewise function is continuous at x equals 1. So to answer this question, we note that for continuity at x equals 1, the following has to be true. The limit of the function as x approaches 1 from the left has to be equal to the limit of the function as x approaches 1 from the right. On the left side of 1, f of x is x squared. On the right side of 1, f of x is kx minus 1. The limit of x squared as x approaches 1 from the left is found by replacing x with 1. The limit of kx minus 1 as x approaches 1 from the right is found by replacing x with 1. And then we solve for k. K times 1 minus k is k minus 1. And then add 1 to both sides. And that's the answer. And this is what it looks like. If we graph the piecewise function, where in the spot where there was a k, we just found that if we put a 2 there, we get the two pieces here. One piece is a parabola, the other piece is a line, but the two pieces are connected at x equals 1. There's continuity at x equals 1 when we made k equal to 2. F of 1 exists. The limit of f of x as x approaches 1 from the left and from the right are both equal to 1. So f of 1 exists, the limit of f of x as x approaches 1 exists, and these two things equal each other. So these are the three conditions for continuity at x equals 1. Now we have a theorem to write down, the intermediate value theorem. Please write all of this down. If f is continuous on the closed interval from a to b, and if w is any number between f of a and f of b, then there's at least one number c in the interval between a and b such that f of c equals w. In other words, if we look at the horizontal line y equals w, and if we have some continuous function where w is between f of a, so maybe f of a is down here, and f of b, so maybe f of b is up here. It's a continuous function. W is some number between f of a. This is the point whose x-coordinate is a, whose y-coordinate would be f of a. This is a coordinate whose x-coordinate is b. The y-coordinate would be f of b. If w is some number between f of a and f of b, then there has to be some place where the function is equal to w. The function can't go from below w to above w without crossing y equals w, or vice versa. So this theorem is used, make sure you write all the words down. Pause video if necessary. This theorem is used to answer questions like this. Does f of x equal x to the fifth plus 3x to the fourth minus 5x to the third plus 2x minus 4 have a 0 between x equals 1 and x equals 2? We will answer this by saying Since f of x is a polynomial, it is continuous for all values of x. You should know that a polynomial function is always continuous for all values of x. Then, since f of 1 would be 1 to the 5th plus 3 times 1 to the 4th minus 5 times 1 to the 3rd plus 2 times 1 minus 4, which comes out to be negative 3. And f of 2 would be 2 to the 5th, which is 32, plus 3 times 2 to the 4th, which is 48, minus 5 times 2 to the 3rd, which is 40, plus 2 times 2, which is 4, minus 4 at the end. This is equal to 40. Since f of 1 is less than 0, and f of 2 is more than 0, by the intermediate value theorem, there is at least one number I don't know what the number is, but I'll call it C, in the interval from 1 to 2, such that f of C is equal to 0. F of 1 is below 0. F of 2 is above 0. There has to be some number between 1 and 2 where f of that number is 0.